So, at equilibrium, all of my energy is kinetic. And then what we could do to find the maximum speed is set our potential energy equal to our kinetic energy. So yeah, that maximum velocity is given by that equation. We could solve for it. But we've done that before, just not with the pendulum. Now, the next thing I want to look at, and for a pendulum, the only way that we're going to be able to get the period is by looking at t equals 2 pi on the square root of L over G. And that's the only way we can get the period of the pendulum. And the only thing that changes the period of the pendulum is the length of the pendulum and the acceleration due to gravity. You can change the mass, you can change the amplitude. That doesn't matter. All that matters is the length of the pendulum. And then here's the energy graph for that. So the kinetic energy, oh, I swapped my colors. Sorry about that. So the kinetic energy is in blue. We have zero kinetic energy at my highest amplitude. And we have maximum kinetic energy when we're at equilibrium. Our potential energy is in red. We have the highest potential energy when we're at position 1 pulled all the way out, and the lowest potential energy back at position 2. In fact, the potential energy graph just looks a lot like the path of the object that it goes. And as before, the total energy is zero. Sorry, the total energy never changes. We get the same amount of energy the entire time, and it's always equal to my maximum potential energy, and it's always equal to my maximum kinetic energy. Now, the last thing I want to look at is the position versus time graph for this motion and all the things that we can get out of it. So, let's draw that real quick. Here's position versus time. We have a couple wavelengths. Couple periods, maximum 3 meters, minimum negative 3 meters. Now, just by looking at the graph, okay, so let's say we have a mass on a spring and the value for that mass is 2 kilograms. Now, just by looking at this graph, we can get some information. So let's look at the stuff we know without making any calculations, just by looking at the graph and looking at these values. The first thing that we know is that the amplitude is 3 meters. That's my highest position above and below equilibrium. Really easy to get. The next thing that we know is that the period is 1 second. Let me trace out from beginning, from where we start, back to that same position takes 1 second. That whole thing takes 1 second. Then we see that my maximum positive velocity, that's where I have maximum positive slope, and we know it's going to be at equilibrium. My maximum positive velocity is where we put those two hashes at 0.75 seconds and 1.75 seconds. My maximum negative velocity is when we're on our way down passing through equilibrium. That's at 0.25 seconds and 1.25 seconds, right there and there. We can also get our maximum positive acceleration. That happens at 0.5 and 1.5. That's the bottom of our path where we're making our smiley face up. And 6, my maximum negative acceleration happens at 0 seconds, 1 second, and 2 seconds. Those are all the things we can know without calculating, just by analyzing the position versus time graph. Now, if we do some calculations, we can get even more stuff with just the things that we know right now. So the stuff we can calculate just from this graph. First thing we can calculate is the spring constant. Well, how can we do that? Well, we know that the period here is 2 pi on the square root of m over k. And we showed this on the first slide. If you solve for k, you get 4 pi squared m over the period. Well, 4 pi is a number 4 pi squared is a number that we can plug in. M we know is 2 kilograms, and the period is 1 second. So we plug all that stuff in, and K is 4 times 3.14 squared times 2 kilograms over 1 second squared. And so that spring constant comes out to be roughly 79 newtons per meter. So boom, just from that graph and knowing the mass, we can calculate the spring constant. The next thing we can calculate is the maximum potential energy. Well, how can we do that? We know for a spring that potential energy is 1/2 Ka squared. We just found K, and we know the amplitude, so we can put those two things together. 1/2 the spring constant, 79 newtons per meter, times the amplitude of 3 meters squared. Boom. So energy comes out to be 355 joules. Really, really easy. Now my maximum potential energy is also my total energy, and it's also my maximum kinetic energy. So I can calculate my maximum kinetic energy. Maximum kinetic energy is the same as the maximum potential energy. Just doesn't happen at the same time. Maximum potential energy happens at 0 seconds, 0.5 seconds, 1 second, 1.5 seconds, 2 seconds. Maximum kinetic energy happens where my maximum velocities are. But it's the same as the maximum potential energy because of the conservation of energy. So we know that the maximum kinetic energy is 355 joules. Once we know the maximum kinetic energy, we can find the maximum velocity. We know that kinetic energy is 1/2 mv squared. So if we solve for v, multiply by 2, divide by m, take the square root, and plug in our number for maximum kinetic energy, we can get our maximum velocity. 2 times 355 divided by 2, square rooted, gives me my velocity. That velocity comes out to be 18.8 meters per second. Because once you have maximum kinetic energy, you have maximum velocity. Then you can get maximum force and maximum acceleration. Maximum force is just K times my maximum position, or K times my amplitude. So that maximum force is the spring constant, 79 newtons per meter, times 3 meters. Maximum force comes out to be 237 newtons. Once we have the maximum force, we can find the max acceleration. Max acceleration, force equals mass times acceleration. Acceleration is force divided by mass. So 237 newtons divided by 2 kilograms. My maximum acceleration is 118.5 meters per second squared. Those are all the things that you can get from the graph. It's just a quick little review of what we've done so far.